Okay, so all week we've learned a lot of formalism and done many mathematical calculations. So for today, I just wanted to show you how those things that you've learned are used in practical models and sort of how it's refined, let's say. So this will be just a presentation to give you a flavor of the current state of the field and what remains to be done in the future. So yeah, what's shown here are just two examples from numerical relativity. Up here is a binary neutron star waveform in blue, and the point after which it gets really interesting is after the merger, once the stars collide and then they do some really complicated nonlinear thing and eventually they collapse to a black hole. And then in the background in black is a signal from a binary black hole, just to show visually how the difference arises. And then on the bottom is the same idea for a neutron star black hole signal. And you see in this case, the main difference or the most striking difference between the signal with the neutron star in it and neutron star black hole is that the and double black hole is that the neutron star black hole signal all of a sudden simply ends. And that occurs when the tidal field becomes so strong that the neutron star gets tidally disrupted. So the material can no longer have enough self-gravity to withstand the tidal force from the companion. So it gets disrupted, and that shows up as a sort of the signal suddenly shuts off. So I will discuss a bit more details of this throughout the presentation, not so much on the post-merger, because I think Nils Andersson wanted to talk about this next week, but you know, about this dephasing during the in-spiral and neutron star black hole a bit. So anyway, let me first remind you where we were at yesterday and how this now factors into what we are talking about today. So we had considered the gravitational wave signal in the leading order approximation. So we were using the second time derivative of the quadrupole moment of the source. We had calculated and found some expression where the strain measured at the detector was given as a function that, you know, depended on how the source is oriented with respect to the detector and so on. So many a function characterizing those parameters, then 1 over the distance to the source, then the amplitude dependent on the chirp mass, which is this kind of combination of the masses, and then it increased with frequency, and it was a oscillatory but sort of increasing frequency, where the frequency was computed by imposing that the gravitational radiation at infinity is balanced by the change in the energy of the binary system. So we could calculate the evolution of the frequency from this energy argument. And neglecting tidal effects, we found some expression like this. Again, the chirp mass showed up and the frequency to some power. So, of course, this was only the leading order approximation, so there will be many corrections due to tidal effects and due to also relativistic effects, because this was just assuming the binary has Newtonian dynamics and the emission is just due to the quadrupole. Yeah, we don't want to calculate that in detail. It can be done systematically in post-Newtonian theory, a perturbative approach. So, but okay, yeah. So, but why? So why is that important to calculate these signals very accurately? So that's when you have these kinds of signals in a real detector, the way the signals are extracted from the noise and also the parameters are measured is by using matched filtering. So the idea is when you have such a chirp signal in the noise, it changes the statistical properties of the output. So if you go in and you have a model waveform that matches this chirp and you sort of it's like doing a Fourier transform. You filter against what's in the data. So when your model matches exactly the signal, then you will get a peak in the signal to noise ratio. So because you're integrating over this entire signal, it's very sensitive to the dephasing. You know, if your model gets out of phase with the true signal, that will be obvious when you do this convolution. That's just a very rough idea, just to emphasize that these experiments are very sensitive to the phase evolution. So even a small difference in phase can be detected. And just very crudely speaking, the way it works is you take the detector output and you filter it against these bank of waveform templates by doing like an integral in the Fourier domain, and that integral is also weighted by the detector sensitivity or the noise spectral density. Very crudely speaking. I mean, it's a whole industry and science to know how to do good data analysis. And I think last year at the school, Satya talked about all this data analysis. So you can go back and see a more detailed talk on this, or more detailed treatment. Okay, so here, this is just to illustrate what is now the effect of adding the relativistic corrections and eventually also the tidal corrections. So this is a signal just for the in-spiral, starting from 30 Hertz, which is roughly where the LIGO sensitivity curve starts. And it's for a 1.4 solar mass system, just the Newtonian signal that we showed on the previous, that we derived last time, essentially. And you see here, as a function of time, it lasts about a minute or so. And it increases in frequency and amplitude. And the phase is just a function of the chirp mass. And we call it 0pn because adding these relativistic corrections means we are doing post-Newtonian theory, which means small corrections to Newtonian dynamics and Newtonian physics everywhere. Okay, so now when we add post-Newtonian corrections, the effect on the phase is the following. So in the very this is the same system. In blue is still Newtonian. In green is now the 3.5 post-Newtonian, which is currently the most accurate model available. We see in the beginning the two still agree. If we were to look in the middle, there would be a small dephasing already between including the relativistic corrections and the Newtonian. And then you see clearly adding the relativistic effects changes the length of the in-spiral, and you don't really see the dephasing, but it's quite a significant effect. And we can write the phase as a function of t always like this leading order term that depends just on the chirp mass, and then these post-Newtonian corrections, and they all come with different powers of the frequency. So, or frequency, or equivalently the velocity that the binary is orbiting at. So you see the first post-Newtonian corrections are order v over c squared. So it means they become only important when the velocity is close to the speed of light. And then higher order post-Newtonian corrections come in when the system is even more relativistic. So here we know currently up to v over c to the 7. And these post-Newtonian corrections now start to also depend on a different combination of the masses, not just the chirp mass, but also the symmetric mass ratio, which is the reduced divided by the total mass. So if you measure both the symmetric mass ratio and chirp mass, you can infer the individual masses to some accuracy. Yes? So Newtonian means exactly this waveform. Newtonian, just using the quadrupole formula, Newtonian amplitude, Newtonian phase computed by this. This is what I mean with it.
2.5
Yeah, 2.5 fractional correction, yes. Okay, and this is all for non-spinning, so, you know, at some point also spin effects come into play, spin-orbit effects, spin-spin effects, and they make the signals much more interesting, of course. But let's keep the discussion to non-spinning for simplicity. Okay, so this is for without tidal effects. Now, let me remind you, we talked, also summarized yesterday, about how tidal effects influence the gravitational wave in two ways. Well, first, some energy goes into the deformation, so there's a correction to the energy. There's also a contribution from the multiple moments of the bodies to the gravitational waves, so that modifies the energy flux. And then we compute phasing in the gravitational waves by imposing energy balance. And so roughly what we found was always these tidal corrections, scaled as the frequency to the 10/3 power. You know, when we took the fractional tidal corrections, it was always omega to the 10/3, and that corresponds to V over C to the 10. So it's even much, much higher sort of relativistic effect than the post-Newtonian effects that we currently know. But it's just, it scales as a high power of V over C, but physically it's a Newtonian effect. And yeah, we also discussed that if you have two extended objects in the system, what influences the waves or any correction is the combination of the tidal parameters of each object. So you see, the key input needed for gravitational waves is to know what these tidal parameters are. And so here are some results for what these look like as a function of the mass of the neutron star for different equations of state. So this shows the tidal parameter as a function of the neutron star mass, computed for various different equations of state, just to get a sense of what's the range of this parameter. And in fact, if you look closely, you will see down here the red curve, SLY. So hopefully by the end of today, you will compute exactly this SLY curve. Yeah, and I should say, so this is shown here starting from a mass of 0, but of course, we don't really expect neutron stars to have mass less than 1 solar mass. And down here, these blue lines indicate the masses of neutron stars and binary pulsars that have been measured. So it gives you a sense of the range. And then the highest mass that has been measured is 2 solar masses. So again, to emphasize how that relates to the equation of state. This is shown in this plot here, and also how it relates to the mass-radius relationship. So you can approximate, in some cases, for some purposes, the equation of state as a piecewise polytropic approximation. So you just say, if you plot the log of the pressure versus log of the density, the equation of state looks almost, to some approximation, like straight lines. In fact, yesterday someone showed me their interpolation and they fitted it with a straight line. Yeah, and so you see these equations of state, like the green one here, that have high pressure for a given density are called stiff equations of state, because if you try to compress them, because they have high pressure, they resist the compressions. They're kind of stiff. And then these that have low pressure at the same density are called soft, because it's easier to compress them. And so you see here then, translated from pressure density to the mass radius curves, the stiff ones have high radius for a given mass, the soft ones, and also high maximum masses, the soft ones have lower. I mean, yeah, I don't need to repeat it maybe. Similarly, for the tidal deformability, it's easier to deform stiff bodies than soft equations of state. So, and it's also not so surprising because we know this lambda goes as the radius to the 5th power. So if you have a large radius, you also have a large lambda, generally speaking. I mean, the K2 prefactor is a bit dependent also on the equation of state, but the scaling radius to the 5th is a good approximation. Okay, so this gives us the parameter that we need to know for gravitational waves. And just as a curiosity or a side, there has been much excitement recently about universal relations between neutron star parameters. So in 2013, Yagi and Yunus came out with so-called I love Q relations, where I means moment of inertia, love means tidal love number, and Q is the spin-induced quadrupole. And what that means is simply if you take dimensionless versions of all these quantities and you plot them against each other. So here they plotted the rotational quadrupole normalized to make it dimensionless versus the tidal deformability also normalized to make it dimensionless. They find for any equation of state that they considered, all of the results lie on the same curve approximately to in fact a very good accuracy. And this is what is called a universal relation, because if you know this curve, then you can take any equation of state and immediately know, if you have one of these parameters, you know what the other is. And so they considered many applications to test GR, to test the nature of these objects, if there are some exotic objects, to relate measurements in gravitational waves to binary pulsar measurements. So there are many possible applications. And since then, some other universal relations were found. I mean, this triggered a lot of effort in the community. And in fact, one of your colleagues is also working on this, he told me. So there's also universal relations to the compactness, which is a bit less universal, and to the F-mode frequency, and so on. You can imagine many other quantities. And in fact, so this also goes back, there had been previous work by Jim Latimer and collaborators. They found some correlation between the radius and the pressure in the outer core of neutron stars. So, yeah, this was just a side thing I wanted to mention because it has branched off and also generated a lot of directions of research. So now back to the gravitational wave signal. Now let's see what happens when we add the matter effects. So in black we now have the 3.5 PN in spiral signal, and in green is now the tidal. And early on, okay, they're identical for a really, really long time. It's only after about, at the very, very end, you see, if the signal is about a minute long, it's like the last few seconds before the merger, you see that a small dephasing starts to develop. And yeah, as we said, the phase is expanded in this way, all the post-Newtonian corrections, then there's nothing for a while, and then come the tidal effects at V over C to the 10th power. But at that order, we don't know the non-tidal contributions. And in fact, yes? Because we don't know the post-Newtonian calculations haven't been pushed to that high order. Yeah. Well, so they're very complicated, especially at these high orders. In fact, it was only recently that people could calculate the 4PN conservative dynamics, because then you run into many problems where some radiation that the binary emitted in the past gets scattered off some space-time curvature and interacts back with the system. And that might happen multiple times, and that's very, very difficult to take into account. Maybe we can have the expert have a comment on.
What you said is not all too complicated. Group direction.
Yeah, but they are also in the amplitude. I'm just considering mainly the phase because that's the most important part to get right.
Like if you add amplitude directions, will it look very different?
No, not very different. Yeah, I don't have the real comparison, but later on I will show you some results of models that also include these amplitude corrections.
But they do contribute.
Yeah, they do contribute. In fact, so you can see it basically, roughly speaking, from this first signal that we derived here. Okay, maybe you cannot. Yeah, so in some sense, because here the amplitude goes like f to the 2/3, but f sort of also depends on this quantity. But I guess that's too simplistic because you also have to calculate the higher multipoles. But you can see that there could be some contribution coming in. Yeah, in fact, I think we had, yesterday we had these amplitude corrections. Yeah, because they came from the second time derivative of the quadrupole, and we always had mu r squared plus some tidal thing factored out. Yeah, one can have that. So there's a general expression for the radiation at infinity in terms of some multipole moments that can then be related to the multipole moments of the binary. Yeah, but it's always at each post-Newtonian order, for example, the quadrupole will also contribute. So it's, I mean, because there will be corrections from the orbital dynamics coming in at that order. So one has to really take into account all the corrections. Yeah, because at some point, so the quadrupole moment that shows up in the gravitational waveform is not exactly the quadrupole moment of the binary. There's some correction. Yeah, probably Cliff Will talked about it in last year's school, if you want to go back to his notes. Okay, so now what had we seen? Okay, we saw the matter effects. Yeah, and one thing I also want to point out is, so because the tidal effects are at such, only when the system is really, really relativistic, very close to merger, so that has two consequences, of course. Well, one is it's a fairly small effect, but also it's kind of separated from all the other effects. So, because in the following sense. So here we know from the Newtonian we can measure the chirp mass. Then, as soon as the 1pn starts to come in, the symmetric mass ratio can be determined. And then, okay, all the other spin parameters start to come in, and only at the very end is the tidal parameter. So, because everything scales differently with the frequency, that sort of lets one also determine the entangle the parameters. I mean, in the sense that this tidal parameter doesn't have a super strong correlation with the chirp mass, for example. But this has to be done, of course, more carefully with data analysis, just to point it out. Okay, so, but also the third consequence is that, of course, at these high frequencies, the post-Newtonian is no longer a very good approximation. So it's, if we want to have a good model for tidal effects, we also have to make sure we understand the point particle dynamics at these high orders. But as we said, the post-Newtonian is very difficult to, and not yet available to calculate these terms. So what can we do? So here is a sort of a diagram for different approaches that we can take to the two-body problem. And it's divided into a parameter space where on the y-axis is the orbital separation, or for these kinds of binaries, also 1 over the velocity. So as you go down in the diagram, the system becomes more relativistic. And on the x-axis is the mass ratio. So, of course, at infinite separation, we have Newtonian dynamics where we can solve the two-body problem exactly. And then, as we said, we put some relativistic corrections and we get post-Newtonian theory. But eventually that also breaks down. We go to the very strong field regime. But the problem is an individual binary will evolve, of course, from small separation to large separation to small separation. And eventually it enters into the regime of comparable masses at small separation where we have numerical relativity. But those simulations are very costly. I mean, it takes weeks to months to just do a single configuration. So it's not feasible to do data analysis for long signals over a wide range of parameter space just with numerical relativity. So another approach that we can take is to start from the test particle limit, because there we know it's a small particle orbiting around a black hole, and we know all the relativistic effects in that problem. So we can again perform a perturbative expansion, this time in the perturbation parameter being the mass ratio, and push it to more comparable masses. But again, that breaks down at some range. So the idea is to have some models, because you see we do have information in different patches of this diagram, to combine them into single models and hopefully improve the modeling. So this is the idea of what is called the effective one-body model that tries to combine all information from post-Newtonian theory, test particle limit, and numerical relativity into a single framework to get an improved description. And there's also a similar approach with the phenom models that I don't know much about, but Ajit is the expert here. So if you have questions, you can ask him. And so I will talk a little bit about this effective one-body model, that how to construct it and what is the general idea. And those two models are the models that are typically used for data analysis. In all the published black hole detections, those models were used. Both of these, because it's also good to have different models to quantify the systematics. So the idea of the effective one-body model is the following. So as we said, the binary problem becomes simpler when you go to the center of mass frame, but here we don't want to go only to the center of mass frame, we want to go to a description where we have an effective particle moving in an effective space-time, because we know in the test particle limit that includes all the relativistic effects. So we start from this test particle relativistic description and say, okay, we want to now map a comparable mass binary onto this kind of problem. So we take an effective particle now with the mass of the reduced mass, and it could also have an effective spin that's moving in some effective space-time, which is constructed in such a way that in the test particle limit it reduces exactly to a curved space-time. And so that space-time is also characterized by the total mass, the total spin, and then the symmetric mass ratio. And away from the test particle limit, the space-time gets, so to say, deformations on the symmetric mass ratio. So if you're looking at this deformed metric, it's no longer a solution to Einstein's equations. But it becomes a solution in the test particle limit and in the post-Newtonian limit. And in between, it just interpolates. So that's what's done in that model. And so instead of having an action, it has a Hamiltonian. It also includes gravitational wave dissipation, some radiation reaction forces, prescription to compute gravitational waves, and finally, for black holes, you know, this kind of effective description works only for the in-spiral. But then we know at the very end of a black hole merger, we have to transition to a final perturbed black hole. So there's just a way to smoothly make that transition to the perturbed final state. And so in addition to all these inputs, there's additional information coming from numerical relativity. So this is shown in the plot here, where on the top you see in blue the numerical relativity result for two black holes with spins, almost the maximum spin, and in red is the EOB. And you see both agree fairly well, but then if you look closely at the end, after maybe 56 gravitational wave cycles since the beginning of the numerical waveform, you see there's a small dephasing development. The merger time is too early for the model and so on. So the idea is then to add a few functions with undetermined parameters to the model and fit the coefficients to numerical relativity data to improve the model. And the hope is you can just fix the coefficients with a few waveforms, then you can use the model over a wide range of parameters and you still get good agreement. That's the hope. And yeah, so once you tune this model, then by construction it agrees very well with numerical relativity. Although I should say that so this model was not tuned to this exact waveform, but to a fairly similar one. Because equal masses, there are many simulations. Okay, so this is how information from numerical relativity is also included.
Can you tell again why that is not matching?
Because it doesn't have enough information about, so let me maybe show this plot here. So currently, in what I described previously, had only information from Post-Newtonian and from the test particle limit. And it had some choice of how to interpolate in this space. But now the numerical relativity gives you information about how to do this interpolation so it's actually closer to reality. So, yeah, it's complicated. So first of all, there are corrections to the Hamiltonian, simply inspired by post-Newtonian. If you had a 5pn correction, you know what it looks like in terms of m over r and so on. So you know how it would scale. So you put a free parameter in front of it. There's some in the Hamiltonian. So in fact, I should say also the post-Newtonian information is kind of resummed in a way, because it always comes like a Taylor series expansion. And this is sort of repackaged a bit so that in a new function, so that once you expand, you recover post-Newtonian. But the hope is to resum it to make it more realistic. But you don't know. Yeah, and in fact, so one parameter in this EOB Hamiltonian sort of changes the location of the horizon of the effective space-time. So that's one parameter for the non-spinning case. Then there are some spin-orbit and spin-spin parameters in the Hamiltonian. And those are for the Hamiltonian, that's it. Then in the gravitational waves, okay, then it becomes very messy because so then, let me see if we can see this. Because so here at this stage, let's say the orbit is no longer like a quasi-circular in-spiral. It also becomes important that there's some radial velocity and so on. So one fixes some so-called non-quasi-circular corrections that are supposed to take into account some larger deviations. And those are they're just fits to numerical relativity so that you recover the correct time at merger or the correct shape of the amplitude at merger, because that's really where the analytical information doesn't give us any insight. So this is we take into account some information about the features of the waveform near merger, basically. Yeah. Yeah, so usually they are functions of the symmetric mass ratio. Yeah. No, the spin is taken into account separately. Yeah, so in principle, yeah, you could say it's like the spin orbit and spin parameters. They're function. If you lump them together, yeah. No, yeah, they're still functions. For each interaction, they're functions only of the symmetric mass ratio. But in the, so there's one more correction in the gravitational wave phase that is put. That is depends also on the spin. So in the dissipative sector, there's much more, or in the waveform, there's much more than in the Hamiltonian. Okay, so now next thing we want to talk about is how to include tidal effects in this model. And for these adiabatic tidal effects that we've considered mainly in these lectures, it's fairly easy. You can show that it simply reduces to adding an additional deformation to the space-time that now depends on this tidal deformability parameter. Basically, you can understand it because in a crude way, because this mapping here, will give you the Hamiltonian, and the Hamiltonian is roughly the energy, so you expect this tidal correction to the energy to come in this way. And then there's also, as you said, the tidal correction to the gravitational wave amplitude. That's also taken into account. And that affects both, so here I said here, gravitational wave dissipation and wave generation. So there's basically, those two are closely connected, so that the wave generation, if you compute the gravitational waves emitted from the system, that gets fed back in and gives you the energy loss, for example. So it's trying to be self-consistent in that. So the amplitude corrections also affect the radiation reaction forces. Okay, yeah, let's see what's the next thing. So we discussed a bit going beyond this adiabatic approximation by including the effect that, in fact, there's a finite F-mode frequency. So we said normally the induced multipole should be modeled like a harmonic oscillator, but we just took the adiabatic limit of it, because we argued that this F-mode frequency scales roughly like the scale of the star, up to, equation of state-dependent things and relativistic effects. And the tidal forcing frequency in a binary is roughly twice the orbital frequency, because basically Eij was always Nij STF tensor, and Nij was cosine phi sine phi. So you get the tidal field is proportional to 2 times the orbital phase, so the frequency is 2 omega. And so that is typically much lower than the F-mode frequency. So that was our argument for first considering the adiabatic limit. So then, but now I'm saying, okay, if we take this effect into account, what happens? So here we see the ratio induced quadrupole divided by tidal field. And in the adiabatic case, it just reduced to the tidal deformability lambda, let's say. And but then, so this is now for a neutron star black hole, mass ratio 2, and a simple equation of state. And the plot terminates at the end of the in spiral. You see, if I take into account this F-mode effect, in the beginning, it's not much of an effect. But then it really starts to grow, meaning the response is much larger than you would expect from just the adiabatic limit. And this enhancement is simply what you would expect for an adiabatic harmonic oscillator that approaches a resonance. you've probably seen this type of factor before for harmonic oscillators. And so even if the resonance isn't fully excited, the fact that it's such a broad resonance, it makes already a non-negligible imprint in this response. Okay, so now comes a rather technical slide, just to remind you of what we had. So as we said, we have to describe this using a harmonic oscillator like Lagrangian. And so I said, when we go to the relativistic action, we have to include factors of redshifts in the appropriate places. And then here, okay, we have the oscillator term in the Lagrangian. Again, we have to put some redshift factors. But now also the frequency has to get redshifted. And okay, I've already written out something here, because in the term q dot squared, going to the relativistic case, I'm supposed to not differentiate with respect to coordinate time, but replace those derivatives with derivatives along the world line of the particle. So total proper time derivatives. And now here I'm using again coordinate time, so when I write out those proper time or world line parameter derivatives, I get an extra term now in the Lagrangian that gives me a coupling between the angular momentum in the tidal deformation to the orbital angular momentum. So there's sort of like a time dragging effect that comes in. That comes purely from relativistic effects. So this is just to say how this picture now changed a little bit, that we at least mentioned in the course. Okay. Yeah, and you can see I've written it here in the LM decomposition. And so this is in the frame of the neutron star, where the companion is orbiting around it from its point of view. And you see when you write out the equations of motion for Q itself, because there will also be some Euler-Lagrange equations for Q, Lm, then you can see there's a sort of a periodic driving force coming from this E, Lm e to the Im phi. And this is sort of where all this enhancement calculation and so on comes from. And yeah, we usually considered the adiabatic limit, where all these time derivatives drop out and we just have the tidal parameter and the tidal field squared. Okay, and let me see if, yeah, okay. So this effect is now also included in the EOB model to improve it a bit, because we saw it should be taken into account. And now let's ask how well does this model now work to describe neutron star binaries. So the first thing we consider is the case there's one neutron star and one black hole, because that's a much simpler system. We just have one extended object. And we're asking now how well does the EOB model work when it is compared to numerical relativity simulation. And this is here now for a mass ratio 2 to 1, non-spinning, very simple equation of state. It's not very realistic, it's more meant to test our model. And so we see the waveforms agree fairly well, but so by eye you don't see much of a dephasing. And when you zoom in at the very end, we can see when we just plot now the phase difference, not the waveform itself, but just look at the phase difference between NR and the model, we see the following. So here is the phase dephasing in radians, very, very small scale, okay. And here is the gravitational wave cycles after the beginning of the waveform. And the cyan region is the error in the numerical simulation, because those are also for numerical relativity. These simulations, including matter effects, are also more difficult than just simulating two black holes. So there is also an uncertainty coming from all kinds of numerical artifacts that is quantified by the cyan region. So anytime a model is within that error region, we say it agrees with the simulation as far as we can tell. And I've shown here in black the phasing you would get from two black holes. So clearly we see that some finite size effects start to matter. And then they're fairly well described by these adiabatic tidal effects up to maybe one cycle, which means half of an orbit before the tidal disruption in this case, or the end of the in-spiral. And when you include this dynamic tidal effect, then the model works, it's indistinguishable from within the NR uncertainty for this particular case. And what's interesting, any questions about this? So what's also interesting for neutron star black hole is what I mentioned before about tidal disruption. So for so that scenario is most favorable when you have small mass ratios, stiff equations of state, or high black hole spin. So all these will help your chances for having a tidal disruption. And that occurs, so you can already think about it. So when the neutron star gets closer and closer to the black hole, the tidal force will start to strip off material from its surface that you can compute simply by force balance. When is the force on a mass element on the surface due to its self-gravity equal to the tidal force due to the companion? But that we don't see any signature of that mass stripping in the gravitational waves. Only when really the core of the neutron star finally gets disrupted, when the central density starts to decrease rapidly, when we see this tidal disruption signal. And that occurs roughly when the total energy in the tidal field is equal to the total self-energy due to the self-gravity of the neutron star. And what then happens is the neutron star gets torn apart, so that it's no longer strongly bound. The material has much lower density. It's also spread out in a more symmetric fashion, so that rapidly damps out the gravitational wave signal. And there's also no ring down signal because sort of each mass element in this debris will radiate gravitational waves at a slightly different phase. So when you add up all the contributions, the phases cancel out, basically. And so this sudden shut-off of the signal could, in principle, be measured, and it again depends on this tidal parameter, because as you see, if you estimate from this kind of energy balance, then the tidal energy will depend on this parameter. Okay, and the other scenario that can happen is when the mass ratio is very large, for example, the neutron star will simply plunge into the black hole, and the waveform will look almost indistinguishable from black hole. And the exciting prospect also with tidal disruption is to look for an electromagnetic counterpart, because then there will be material, maybe some accretion disk, maybe a short gamma ray burst. So these are the more interesting scenarios. So just to summarize, for the features in the signal, that for non-spinning systems, for a really long time they're like point masses, then tidal effects lead to a small dephasing. Finally, there's tidal disruption or not, could be just a plunge, and this could possibly also be measured. Next, of course, more promising to measure tidal effects would be a double neutron star in spiral, because then you have contributions from both objects. And this is shown here, where on the top I show the snapshots just from the simulation of at different times of the density distributions. So the red means it's higher density, and these are the two neutron stars, and blue means low density. But one has to keep in mind, okay, these are just some snapshots from the simulation. There's a lot of gauge dependence. There could be, because also the slicing, they always do a 3+1 decomposition into time and space. The slice could be weird, so this is not a physically observable representation. It's just to give you some idea of what the neutron stars are actually doing, but it has to be taken with a bit of care. So here again is the signal, gravitational wave signal versus time. And you see NR and tidal EOB. In the beginning, they agree fairly well until this is the blue corresponding to the blue picture here. So they're still isolated, not much deformed. So yeah, we would expect the model to work pretty well. Then later on, we get to the green, which corresponds to the second picture. There's already some parts of the upper layers are starting to come into contact. So this is roughly the point after which our models start to not work so well, because then the cores of the neutron stars are still fairly compact, and they keep on moving through the material that used to be the outer layers of the neutron star until they finally collide and merge. And so one thing you notice is when the stars come into contact, there's no feature in the gravitational waves, so we don't really know when exactly the contact occurs. It's really only when the cores collide that we see this peak in the gravitational wave amplitude, which is shown as the red here.
And that would still be the final configuration?
Yeah, yeah.
And what would you expect from that?
Yes, so, okay, I'm not sure if I have, so I have only one example, but I would expect this type of signal, because it's basically, it will be rotating and also oscillating, and so it will be a really interesting signal. And so this is just one example, but the signals could look very different depending on equation of state or parameters. So this is where it gets really interesting, but unfortunately that's the region that's kind of outside of LIGO's most sensitive band. But for third generation detectors, this is a key target.
When you come to late stage where it is in contact, so
yeah.
would it cause a supernova explosion or something?
Yeah, it might cause a short gamma ray burst. In fact, yeah, people think that's one of the most promising mechanisms.
So will that have an effect on this? So the map is gone out?
Yeah, but you wouldn't see the burst itself in the gravitational waves. It's just the matter is flung out, and whatever remains in the center is generating gravitational waves for the main signal, and the burst can happen without impacting the signal. Okay, let me just go back here, because I wanted to show again, we can also look at this, instead of looking just at the waveform, which is not so informative, we can look at the dephasing. So here's again the phase change, this time plotted as a function of the frequency. And you see clearly, here these columns correspond again to these snapshots. You see clearly after the green column, the black hole model is completely different. The adiabatic tides is a somewhat better description, and the dynamic tides is also even better yet. But still, as we said, after the stars come into contact, there seem to be some physics missing from the model. It's not clear yet how that will impact detection and everything, or well, detection probably not, but parameter estimation, but that's just something to keep in mind. Also, this is for a very stiff equation of state. So for softer equations of state, the models work much better. Okay, yeah, this was just to summarize. what happens, because I think next week Nils Andersson wanted to talk about this post-merger phase, what exactly happens and so on, so it should be quite interesting to hear. Yeah, in any case, we know there's a rich characteristic frequency spectrum and also some multi-messenger counterparts. Yeah, because also these mergers are thought to be the at least a big factor or a big production of our process elements, which are heavy elements. So this will also happen, and yeah, many interesting things to be studied. Okay, so now what I've talked so far were mainly theoretical predictions. So now I want to mention, you know, how can we use them and what do we expect to extract from these tidal effects. So as you probably know, there's currently and in the near future will be a worldwide network of gravitational wave detectors, the two LIGO detectors in the US, then advanced Virgo, which is also going to join. Then in Germany is a really small detector just to test some technology. And then, of course, in India, we hope to have another detector very soon also, in the next few years. And then there's also a detector in Japan called Kagra that also uses new technologies like cryogenic cooling of the mirrors to reduce noise and so on. And so having this kind of worldwide network is really important if one wants to look for an electromagnetic counterpart to the gravitational wave signals, because it really helps to localize the sources in the sky. And also, of course, it improves detection confidence, and it can also help estimating parameters, because the more detectors you have, yeah, if they have the same sensitivity, that would help. And if you want to measure some information from the polarization of the waves. So for testing general relativity, this is quite important to measure the polarizations. And then in the future on Earth, people are talking about various upgrades to LIGO to make it much more sensitive. There are some ideas to have a 40-kilometer arm detector called the Cosmic Explorer. And then in Europe, they might build what is called the Einstein telescope, which would also be much more sensitive, 10 times about more sensitive than LIGO. And there are various other ideas floating around. And of course, also LISA will be in space, a mission in 2030. But in terms of observing waves from neutron stars, it's more the ground-based detectors that will be the main, will give us the main science. Okay, so you might say, okay, you've heard about 3 black hole detections, but no neutron star detections yet. But that's also not so surprising because of the following. So the black hole detections that were found, they were at large distances and had large masses, so they could still be seen. But the neutron stars, they have kind of low masses, so we saw before the amplitude of the waves goes like the chirp mass. So for neutron stars, we cannot see them out to very far distances. So here this shows you roughly the volume of the universe where LIGO could see neutron mergers. And in blue is, in yellow is what the initial LIGO do. But then there was a major upgrade to advanced LIGO. So the pink is where advanced LIGO was sensitive to. And currently, you know, it's still in that sort of range. You see it's just a very small volume of the universe. And as you will probably hear next week, we don't expect too many sources to be in that volume, because we know a handful of neutron star binaries in the galaxy and nearby, but they're all at such large separation that they would merge within LIGO's band anytime soon. So we really need to be lucky and have a source that is close to merger within that volume. But then the plan is, of course, to keep upgrading the detectors, and then you see once the design goal is reached, LIGO could see intervals of neutron stars from maybe a million galaxies, and then the chances become much better that there will be a signal. So this is just to motivate why it's still interesting and will be an interesting prospect. So now, what can we expect? How can we measure this tidal effects, or how well can we measure it? So there have been several studies now to date. They all had some caveats, so you have to take all these results with a grain of salt. These are just some, to give you a ballpark idea of what could be possible in sort of more optimistic scenarios. So the first study that I want to show, so there have been many, but I'm going to show two examples, okay? So one is from Lackey and Wade in 2014. And so what is plotted here is the tidal deformability again as a function of mass. And they loaded in some prior information from causality and maximum mass constraints and those things. And then asked, suppose the equations of state we have are these black solid lines with LIGO at design sensitivity, a year of data, and with assuming an event rate of about 40 events per year, what can we say? How well can we measure it? And that's the uncertainty in the measurements that they found is shown as these shaded contours. Around each lambda of M curve, they drew the shaded contour to say how well can it be constrained. So it doesn't look too bad. Of course, there are so many, this shows just a few selected equations of state, but there are so many different equations of state you could have. I mean, you cannot really say this measures exactly the equation of state, but it at least constrains it. And yeah, when you translate this to equation of state, again, people show usually the log of pressure versus log of density. They find these kinds of contours. And I think, yeah, here the blue is for the loudest, is the 3 sigma, green is 2 sigma, and the red is 1 sigma. Yeah, because they had a similar plot in the paper saying where does all our information come from, and it turns out it's probably the 5 loudest events, and then you do a little bit better if you have more events, but not so significantly. And yeah, so similar conclusions are also obtained by other analyses, with of course also caveats and assumptions. And also for neutron star black hole systems. And another way to present those results is to ask, okay, you have the deformability now on this side, but because, okay, let me go back actually. So you notice here the range of deformabilities that you're really interested in is just from 1 solar mass here to the maximum mass here. And you see the lambda of M curves are almost linear in that regime. If you cut out the early part below 1 solar mass, you see these are almost linear curves. So what they did in the second analysis is to assume a linear fit to this lambda and then just constrain these fitting parameters. And this is what's on the y-axis here. And they just considered 3 different equations of state. One was a very stiff one, MS1b, no MS1. Then intermediate one, H4 in green, and in red is a strange quark matter equation of state. And they ask, okay, we want to measure this parameter, how many events, after how many events can we distinguish these 3 classes of equations of state? And this is what they plot here. So as you accumulate more events, you get better and better constraints, or you become able to distinguish them. Again, caveats, but Yeah. Questions? Okay, so this is just to say, so in principle, some information can be obtained. It won't be a precision measurement, but also depends very much on the signal-to-noise ratio and other things. Okay, so now I'm already onto remaining challenges. Sort of what remains to be done, because this continues to be an active area of research to model double neutron star and neutron star black hole binaries. So of course I mentioned the late in spiral after the stars come into contact in binary neutron stars. Neutron star black hole near the tidal disruption when there's already some mass loss. There is some, in some cases we see that the models could be improved. Then the other thing is to get a complete model that includes also the post-merger physics. But that's of course very complicated because, you know, during the in-spiral the system is still quite clean and things, but once you go to the merger and post-merger, all kinds of microphysics, magnetic fields, possible shocks and instabilities start to become important. And you know, that's also not well modeled with numerical relativity at the moment because there's just too much microphysics to take into account. But ultimately, I mean, with current numerical relativity simulations, there are some ideas, given the physics that is put in and the numerical resolution that they have, they can produce a post-merger model, and at least one could use that for data analysis instead of having nothing at all. And also the tidal disruption for highly spinning systems. Currently, there is a model for tidal disruption, but just for moderate spins, moderate aligned spins, so that could be improved. Then, of course, one has to continue to test and improve models. That is crucially dependent on having increasingly accurate numerical relativity simulations. Yeah, we have to include more realistic physics, quantify systematic uncertainties, optimize the models for data analysis, and then figure out, you know, how, given a measurement of this lambda parameter, how do we tell nuclear physicists what our result means for them in the most efficient or best way. Next, yes, a big topic is to add the spins of the bodies. So in the models we currently have, spin effects are included, but just for point masses. So our task is a bit simpler. We only have to include those spin effects that are spin matter effects. So, but there could be then new phenomena that come in. So first of all, those are already known. Then the spins will shift the mode resonances, so it will shift the F mode frequency and all the other mode frequencies. There are, of course, many new tidal interactions and love numbers. Some of them are quite small. There have been some studies on this already to explore, but others were found to be quite important. So that has to be taken into account. Then also gravitomagnetic effects that I mentioned briefly, where the gravitomagnetic field induces current moments in the neutron star. There was some recent work. So in general, those effects are quite small. So we didn't currently include them. But recently there was some work to show that in those gravitomagnetic effects, there's also an effect that it has a zero frequency mode. And so it induces a velocity perturbation in the neutron star that just grows with the frequency. So it's not clear what effect that will have on the gravitational waves, but that's potentially important. Then there was some concern that there could be some nonlinear interactions between different modes in the neutron star that could lead to instabilities very early on in the in-spiral and then produce a huge effect on the gravitational waves. So it's a coupling of different modes inside the neutron star that then go unstable and absorb energy, so that changes a lot of properties of the system. Then, of course, yeah, as you will hear next week, a neutron star has many, many different modes of oscillation. So potentially they could all get, well, depending on their frequency, those with low enough frequency could get excited during the in-spiral. And so there were studies already in the 1990s to show that the effect of those modes is fairly small, but this has to be updated with including superfluidity, which changes the mode spectrum, and using relativistic in-spirals, not Newtonian. So this should be quantified. And then, yeah, one could also include the effect of orbital eccentricity. And yeah, this is by no means a comprehensive list. So there's still quite a lot of work to be done. And yeah, this already gets to the end. So just to summarize, in general, gravitational wave detections of neutron star binaries and neutron star black hole are expected in the next few years, and everyone is quite excited about them because they will bring new phenomena as compared to the black hole observations that we have seen so far. And yeah, we will get a wealth of new insights into the astrophysics of neutron star binaries, the nature of gravity, and the central engines of gamma ray bursts. And at the merger, it's not only the gamma ray burst, but then there's all kinds of other emission that you see in the radio, in X-ray, in optical, long afterglows. So there's a lot of excitement also to look for those. Because maybe the gamma ray burst, you only see it when the beam is pointing towards your telescope, but this other afterglows you might see might be more isotropic, and so you have better chances of catching that. And then, yeah, the most readily accessible information about neutron star matter will be these tidal effects, at least in the next few years, what you can expect. And to take full advantage of this requires that we have accurate theoretical descriptions for it. And so I described a bit what the current status of models is and how we include these effects. And those have to be tested against numerical relativity simulations. And there's still some remaining work to be done. And one goal of all this effort is also to envision the science case for future instruments, because it always takes time to go to the funding agency with a completed proposal and get funding. And so if we want to have some third generation detector in 10 years from now, so we have to start really putting together a more concrete science case to propose exactly. So that's all I wanted to show. So any questions, comments? The dynamical tide takes into account the effect of that there's a finite mode frequency associated with this quadrupolar deformation. And the adiabatic assumes it's just a static deformation that just tracks the tidal field. Yeah, that's in principle there, but it turns out in most cases the resonance doesn't fully occur. It gets close to resonance, but then it merges. This, if it's a two neutron star binary. But it could be for different, it all depends on the choices of parameters, and not all the parameter space has been explored. It's probably more promising to excite the resonance in neutron star black hole systems, because those are more relativistic, so you get to higher frequencies potentially before plunging or getting tidally disrupted. It as the spin-induced quadrupole moment. So it's different. So we always assume the tidal effects and spin effects are not strongly coupled, because for us, the spin, even if it's 22 millisecond, is quite small in terms of dimensionless spins.
Yeah, that I understand. All I'm asking is,
yeah.
if I, let's say, for matter to it, the Earth is spherical or highly oblate? That's the question. Not
Yeah, so in our approximations, we assume it doesn't matter. That's our assumption.
15 kilometers easily.
Mm-hmm.
It will be the size of the neutron star.
Mm-hmm.
So does the thing end there when it comes to the last stable orbit? Do you expect anything further to happen?
Yeah, because of the dissipation, it just goes through. Yeah. Yeah. But then the question is, if it gets tidally disrupted, does that occur before the last stable orbit or already when it's on the plunge part?
Detection of neutron star binary.
Yay!
So within advanced LIGO itself.
Yeah.
Do we expect to see the tidal
No.
things there?
No. One needs about a signal-to-noise ratio of around 25 to see those. And
We have to wait for the next. We have to wait for the third generation.
No, even with second generation, it should be possible. I mean, depending on the event rate, always. But presumably, the first detection would be at the threshold. Yeah, and for that, we wouldn't see it. But maybe after a year, we might have an event at such a signal to noise that it could be. No, because the idea is to make the corrections to the model just in a way to preserve the known physics. And so that you always recover the known test particle and post-Newtonian cases. But yeah, this tuning does get a bit messy, but you can just view it as taking into account numerical relativity information that we don't have otherwise any access to. But because it also has to be done in a way, you have to make sure you're changing only this last part, because here early on the model is great. So yeah, it requires a bit of playing around. Yeah, as I said, so 3 in the Hamiltonian. 1 changes the size of the horizon in the effective spacetime. 1 changes the spin-orbit interaction, 1 the spin-spin. And then there's a parameter for spinning things in the gravitational wave phase. But then there are some hidden parameters. So first of all, there's a prediction from numerical relativity given an initial binary configuration, what's the mass and spin of the final black hole. So that goes in. Then these features near the merger, how they look like, what's the slope of the amplitude and frequency. So that goes in, but it's not encoded in a single parameter at that stage. It's a sort of a fit over many numerical waveforms. So yeah, it's hard to quantify exactly parameters. But for the Hamiltonian, it's pretty clean. Yeah, so for extreme mass ratio binaries, you actually You could do EOB, but it wouldn't be such a good description, because for extreme mass ratio, you are in this regime where you have black hole perturbation theory. And that means sometimes it's also called gravitational self-force, where you have a small object and you approximate it as a test particle in the 0th order approximation, but then you take into account the effect that it creates a space-time distortion due to its finite mass, because it's not exactly a test particle. And then what is the effect of that distortion that it creates on its own motion? So that's called gravitational self-force. And it's actually, post-Newtonian, as we said, we have now 4 PN in the conservative, 3.5 in the phasing, but the self-force we have only to first order, because you have to do relativistic perturbation theory. It's also quite, but this is needed for extreme mass ratio in spirals. Yeah. Yeah, by construction, it has to match all the known post-Newtonian terms and all the test particle limit terms during the in-spiral. Thank you.